So picking up where we left off, we're going to be looking at atomic structure. So we're going to be talking about atoms and their structure. All right. So we're going to talk a little bit about the history of the atom, not necessarily the actual history of the atom, but the idea of the atom. So the idea was actually around 400 BC, an ancient Grecian idea, Grecian. It was two guys, Democritus and Leucippus. They were Greek philosophers. Most people have not heard of them before, but they're the ones that actually came up with the atom. So basically, I always make the joke saying they were looking at the beach, kind of chilling, doing nothing, wearing their togas. They saw that the beach was made of sand, and they said, okay, let's just cut that piece of sand in half, and what do you get? And you get a smaller sand. And so what happens if I cut that piece in half? And so forth and so on, until I get down until I can't cut it any further. And of course, the smallest possible piece would be atomos, which is actually Greek for not to be cut. So that's where the name atoms come from. Now, there was this other Greek, his name was Aristotle, and of course, most people have heard of Aristotle. In fact, they've even heard that he said all substances were made up of four elements: fire, which is hot; air, which is light; earth, which is cool and heavy; and of course, water, which is wet. And if I blend those four things in different proportions, I can make up everything else, right? So that was Aristotle's ideas in those days. Now, who was right? Well, because Greek society was slave-based, that meant these guys did not have to go into a laboratory and prove any of their ideas. So basically, they would say it's beneath famous to work with your hands. They don't do any kind of labor whatsoever. And of course, being in the lab looks like it would be labor. And so what they would do is, instead of actually proving using any kind of logic their concepts, what they would do is simply argue. So it'd just be, arguments back and forth, which is great for our legal system, but horrible for scientific method. But anyway, they argue back and forth. And of course, whoever was more famous, that's who's going to win. So Aristotle had a bigger following. More people believed what Aristotle would say, whether he could prove it or not, didn't matter. They just believed whatever he said. And so he won. Now, his win, of course, was a loss for all of us, because now what's going to happen is all the ideas that he was wrong about are going to carry all the way through to the Middle Ages. And in the Middle Ages, we run into alchemists. And of course, alchemists, all those famous stories, kings would hire them to try to change lead into gold, which we know now can't happen. So all of those alchemists signed up basically to get themselves killed because they didn't stand a chance to be successful. All right, so who's next? Well, it's not till the late 1700s when John Dalton comes along, and he was an English school teacher. It doesn't really matter what he did. What's going to be important as far as what do you need to know is that he came up with Dalton's atomic theory. Now, Dalton's atomic theory is really the first scientific piece of what's going on with the atom. And so what he did was he said, you know what, I'm going to combine the ideas of elements, where we have these elements that have to make up everything, and I'm going to combine it with the idea of the atom, and say that's got to be these individually little pieces that can't be cut any smaller. And so he came up with his atomic theory. Now, you don't need to memorize each and every one of these postulates. However, you do want to understand them and be able to pick them out. So if I gave you, say, a multiple choice question where I said, one of these is incorrect, you should be able to pick it out. Or if I said one of these is correct, you should be able to pick it out. So you need to understand them conceptually, but you don't need to necessarily be able to, give them back to me or write them out or anything like that. So the first postulate, he says, all matter is made of tiny indivisible particles called atoms. So all matter is made of these tiny little indivisible particles called atoms. And that's actually still true today, right? We still refer to them as atoms. In fact, it's atoms and their properties and how they're made up. That's pretty much the whole piece of these segments for this chapter. The second postulate he came up with was atoms of the same element are identical. Those of different atoms are different. So here what he's saying is that all oxygens look the same and all carbons look the same, but oxygen does not look like carbon. Now that one is partially true. I want you to go ahead and make some sort of mark here. You can double dagger it if you'd like. but we're going to want to mark that because we're going to come back to this idea a little bit later. Now, his third postulate was atoms of different elements combine in whole number ratios to form compounds. All right, so atoms of different elements combine in whole number, and we've seen that, whole number, individual particles, and whole number ratios to form compounds. So here what he's saying is I'm looking at water. Water is H2O. There are 2 hydrogens and 1 oxygen. So there's no partials here. It's not H2.4, O1.1, right? They're whole number ratios that make these up. Number 4 is chemical reactions involve the rearrangement of atoms. There are no new atoms that are going to be created or destroyed. And of course, if we omit nuclear chemistry, that is still true today as well. So even today, we cannot create or destroy atoms unless it's a nuclear reaction. And of course, all the reactions we'll be doing and looking at up to this point will be non-nuclear reactions. Okay, so not bad, right? 3 out of 4. If you could hit that many baseballs, you would be a billionaire, basically. And so here it is, hundreds of years later, and Dalton's atomic theory is still holding strong. All right, so again, we're doing a little history of the atom. So Dalton's atomic theory set the stage. There's a couple other big names that come through. We're not going to worry about those here, but they start to develop the atom. One of them is Thomson's cathode ray tube. Now, Thomson, who I believe is in your textbook, but is not somebody in your syllabus that we're required to learn about, he came up with the plum pudding idea of the model of the atom. And so Rutherford is an experiment we want you to know about. And Rutherford, now it's all the way to 1910, so it's been 200 years. Now, Thomson, who I was just mentioning, he probably started working on these things in late 1800s. And Rutherford actually worked for Thomson. So he believed in this plum pudding model of the atom. Now, for us as Americans, we probably have no idea what plum pudding looks like. However, what we can use is the chocolate chip cookie model. So if you think of a chocolate chip cookie and you have the dough is going to be positive stuff, and then the chocolate chips are electrons, okay, because Thomson had found the electron. So he's responsible and gets the credit for finding the electron. And so now Rutherford's coming along working for Thomson, and he says, you know what, how big are those electrons? I want to know. Now, again, there was a couple other names. There's Millikan who did an oil drop experiment, and he's the one that came up with the size of the electron. So we knew the particle, we knew the size, and then we tried to figure out, or at this point they're trying to figure out just how big these atoms are and how big the particles are inside. So what's going to happen here is Rutherford is going to use radioactivity. He's going to use some alpha particles, which are going to be positively charged pieces given off by uranium. Okay, so he's going to have these alpha particles and he's going to bombard a piece of metal. Now, this metal is not just any metal, it's gold. And the reason why he's using gold is because if you're familiar with gold leaf, like if you head over to, can't think of the stores now, Michael's or AC Moore, you can pick up some gold leaf and it's a really, 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 really thin piece of gold. So it's gold metal that's been hammered down to where it's paper thin. You can actually see through it. In fact, if you hold the piece of gold foil up and the wind comes by, it'll just rip it all to shreds. Okay, so that's how thin this gold foil is. Now, what Rutherford's going to do is he's going to shoot that foil with some alpha particles, some radiation. So what's going to happen is after the particles hit the gold foil, they're then going to go somewhere. And so what he's going to do is he's going to surround his whole experiment with some fluorescent screening. I don't know that it's actually page 97 in the most recent textbook that we're using, but somewhere in that chapter there's going to be a picture that looks sort of like this. It's probably a little more artistic than mine, but it's still the same idea. So here we're going to see that we have a lead block with a piece of uranium in here carved out like a barrel of a gun so that we can control the alpha particles and make them head towards the gold foil. And here we have the gold foil, and of course we have that fluorescent screen. So now the particles will hit the gold foil, they'll bounce off, go somewhere, or go straight through and hit the fluorescent screen, and we'll see where they're going. Now, his expectations. So when he started this experiment, he's expecting the alpha particles to pass straight on through without much change in direction. Now, why is that? Well, that's because these alpha particles are big particles. They're like 18-wheelers of particle world. And so they're rolling right on through, and he's expecting that all by themselves, these positive charges and these electrons that are in the atom are not going to be enough to stop these big alpha particles. So it'd be like a motorcycle trying to stop an 18-wheeler, right? He's expecting it to just shoot right on through. Oh, I don't think the noise came through, but that's all right. Make sure it doesn't blow your eardrums out. All right, so what he's expecting is because those particles are smaller and the electrons aren't that big, they won't be able to stop any of the beams. And so all the beams will just blast right on through. All right, so here's the experiment. Here's what he actually saw. The majority of the beams did come straight out. Okay, no big deal there. That's what we expected, but not all of them. Then there were some that ricocheted off small angles. All right, that's to be expected, right? I mean, 18-wheeler hits a motorcycle. Most of the time it's going to run straight through, not change direction much. Other times it's going to hit and veer off to the left or veer off to the right. Just depends on the angle of incident. No big deal there. But however, there were some other particles that were making some marks on his fluorescent screen. And those angles got really wide, which kind of raised his eyebrow. What's going on there? But then the ones that really shocked him were the ones that bounced right back. So now, in your mind, what you should be seeing is an 18-wheeler hitting a motorcycle and bouncing backwards, and the motorcycle not moving. And I think if we tried this experiment 1,000 times out on Route 1, had a nice long stretch, let those 18-wheelers get up to 65, 70 miles per hour, and then smack a motorcycle, I don't think we're going to see one case where the 18-wheeler bounces off and the motorcycle sits still. I think we'd ought to agree with that. So he had to come up with some way to prove or explain what he's seen. And so what he suggests is that the atom itself is actually mostly empty space. Now, in the center, there's a small, dense, positive piece. Now, we've come to learn that these are protons, but that's not what he found in this experiment. So don't confuse that. In this experiment, what he's doing is saying there must be a nucleus in the center of this atom, and it's got a positive center. And so as alpha particles come near this nucleus, that's when they're going to bounce off. So as long as the beam doesn't come near that nucleus, they pass straight through. If it gets kind of close, now remember it's two positive charges, so that positive alpha particle is being pushed away and repelled by that positive center. And if it comes right at it, straight ahead, that's when it's going to get deflected and make it come right back at us. And of course, if it's almost dead straight ahead, that's when we're going to get those big angles. So again, if it's mostly empty space, the majority of the beams are going to pass right through, not hitting anything. Okay, now that's led to pretty much the modern view of our atom. So in our modern view of our atom, we think that we believe that, or we can prove nowadays, that the atom is mostly empty space. Okay, we break it into two regions. The first region is the nucleus, and that's what Rutherford's gold foil experiment discovered. So he discovered the nucleus, and in the nucleus we have protons and we have neutrons. Now the second region is going to be the outside of that nucleus. So there'll be so we have the nucleus, center, then we're going to spread out empty space, and then on the outside we're going to have this electron cloud. So it's almost like the Earth with the clouds above us. Okay, so if the core of the Earth was the nucleus, the clouds on the outside, that's what would be our electron cloud. And this is the region where we may find an electron. That's a little weird statement, right? But that's the modern view. So we're going to work our way through history talking about each one of these particles a little bit. And so hopefully we'll make some more sense out of that. But right now we're just going to leave it at that. We're going to say, okay, you might be able to find an electron in the electron cloud. Now we've discussed density. So we know that density is equal to mass over volume. And so how does that relate to this? Well, since most of the particles went through it was mostly empty space, the majority of the atom might not be that dense. Because the pieces turned so much, the positive pieces were heavy. So in other words, that means all of the mass must be in that nucleus. And so the density of an atom, really, it lies within the nucleus. Okay, so the nucleus has a really, really, really small volume, which means it has a really, really, really big mass. And of course, we know that that means we're going to have a really big density. Now, that small dense positive area, again, is referred to as the nucleus. So again, this is the third time I'm saying it, so don't get confused. The center of the atom is what was found in Rutherford's gold foil experiment. And what he discovered, he calls the nucleus, which is what we call it still today. All right, so what do you need to know about particles? Well, for your particles, what I'm going to need you to know is electrons are represented by an E minus, and we'll be using those quite a bit. So you're really going to get to use those. You'll get the hang of that pretty quick. It's pretty self-explanatory as well. So it's an E raised to the -1, and that's because we know our electron has a -1 charge, right? Protons are going to follow suit. It's a P with a positive charge in the superscript. Now you won't see that used as often, to be quite honest. So I wouldn't worry about committing that to memory. But again, it makes logical sense. We're using the first letter of the word and then the charge that we find on the proton. For the neutron, it's a little n, again, first letter of the word, but then a superscript of 0 because it's neutral. So as I said, the charge of an electron is a -1, proton +1, neutron is 0. The relative mass. So the relative mass for an electron is 1 over 1840, which if you plug that into your calculator gives you 0.00. So we're just going to say that the mass of an electron, it's pretty much 0, okay, even on the relative mass scale. Now for the relative mass, a proton has a value of 1. Okay, we're going to call that 1 AMU, atomic mass unit. Okay, so protons are set at 1. Everything else is relative to that 1. So that's why electrons still don't have any mass. So an electron compared to a proton, electron's still really small. Neutron, also a 1. So neutrons, very similar to protons, but they have no charge. Now, that's all you really need to know about the particles. But at the same time, because a lot of people are new to chemistry, try to point out how small these things are. So when we look at the actual mass of an electron, which we can now have been able to prove, is 9.11 times 10 to the -28 grams. Now, unfortunately, this semester, but maybe in future semesters, you'll get a chance to come into the lab and use the scale. Again, this semester you won't be able to. But if you were able to look at that scale, you would see that it reads 0.000 grams, which would be 1 milligram. So our scales are able to go to 1 milligram, which is 10 to the -3. This is 10 to the -28, so you need 25 more zeros to be able to measure that electron. Okay, so it's super small. Protons, 1.67 times 10 to the -24 grams. So even though they're a lot bigger than an electron, to us as humans, still very small mass, right? You can hold tons and tons and tons of them if you want to feel really strong and make you feel better. Neutrons, of course, have the same mass, okay? Now, the structure of the atom, again, I pointed out there are two regions. We have the nucleus. Inside the nucleus, we have protons and neutrons. Since we have protons and neutrons, if we look at charges, overall, we have a positive charge. Since the protons and the neutrons both have big masses, we can say almost all of the mass is going to be in the nucleus, right? And then the electron cloud, which is our second region, will contain most of the volume. So it's like a marble, where the bigger the part of the volume is way out here of the marble, that's where the electron cloud is going to be. And of course, we're going to find out that's the region where an electron can be found. Okay, so this is a great place to take a little break. So we're going to stop here, and next we're going to get into the size of an atom and then start looking at what we call isotopes. All right, so enjoy, take a little break, maybe get a little snack or something, and then come on back and we'll finish out this section. All right, have a good day.